Hello everyone. This video follows up on the previous two videos about playing notes and forking functions, so if you haven't checked those out, you should definitely check those out first. The goal of this video is to get you comfortable with how tempo works in SCAMP. But in order to talk about tempo, first we have to have some music whose tempo to change. So I've created a short script here to play some microtonal oboe music. Let's take a listen. Now a lot of this should look familiar, but some parts might look a little unfamiliar. Here we're making use of the random library, one of the built-in modules of the Python standard library. And we're using three different calls within that library. The random.random function. This gives us a number between 0 and 1. Random.uniform, which gives us a number between the two numbers that we give it, so here 0.4 and 0.9. And random.choice, which takes a list or other kind of collection and gives you one of the items in that list. So in this case, we have a list of pitches that we're using. This is a kind of acoustic scale with the 11th and 7th partials tuned appropriately. And each time we play a note, we're picking one of those pitches at random. If you've never seen it before, this kind of method might look a little unfamiliar. What we're doing is we're generating a test number between 0 and 1. If that number is less than 0.7, which is going to happen 70% of the time, then we play a short note with a random pitch and random volume. If it's not less than 0.7, then it's somewhere between 0.7 and 1.0. And so when we're testing whether it's less than 0.9, that corresponds to a 20% chance. So 70% chance that we run this code, 20% chance that we run this code. And the remaining 10% of the time that we get a number between 0.9 and 1, we'll run this code that waits. If I wanted to change the character of the music, I could change this to a 0.2, meaning we don't do short notes very often. I could change this to a 0.6, meaning that 40% of the time we do a long note. And then the remaining 0.4, another 40% of the time, we would wait. So this should be slower, sparser music. Okay, I'm going to return to the original probabilities here, and now we can talk about tempo. So if you remember from the second half of the video on forking functions, tempo is a property of a clock, and session is a clock. A session is a clock. So if we want this to go faster, we can change the tempo. s.tempo equals 150 will make it go considerably faster. Whereas s.tempo equals 30 will make it go considerably slower. Something that might be relevant to know later is that actually there are three interconnected properties regarding tempo, and you can set either one that you want. Tempo is in beats per minute and is the most natural for musicians. There's also rate, which is in beats per second. So a rate of 3 corresponds to a tempo of 180. Let's take a listen to that. And then there's beat length, which is just how many seconds long a beat is. So if I were to set s.beat length to 3, that would correspond to a tempo of 20, since each beat lasts 3 seconds long. Anytime that you set one of these three properties, it automatically sets the others to be in agreement. So for instance, if I were to print s.tempo, we would see that it prints 20. Okay, so this ability to set tempo is great, and we could actually fold it in here. Anytime that the oboe waits, it's kind of the end of a phrase, we might set the tempo to something new by writing something like s.tempo equals random.uniform 40, 200. Let's take a listen to what that sounds like. So that's great, but what if we wanted to change the tempo smoothly? Well, the way that you would do this in SCAMP is you can use a function called setTempoTarget. And any clock is capable of doing this. So if we start typing s.set_tet, we see setTempoTarget and setTempoTargets as an option. Now let's look down here at the API at what we need to give that function. setTempoTarget. And there it is right there. So it expects a goal tempo, a duration of how long it should take to reach that tempo, and a couple of other mysterious parameters like metric phase target, duration unit, truncate. If the curve shape argument looks familiar, it might be because it came up in an earlier video in the context of envelopes. As it turns out, tempo in SCAMP is controlled by a tempo envelope. So it's no surprise that a curve shape argument should show up. So let's try this out. Suppose that we want the tempo to start at 40, and then to gradually get faster over the course of 15 beats. So let's go to the tempo of 200 in 15 beats and take a listen to that. You can hear it starting to get faster. And at this point, it's probably made it there. If it feels like that accelerando happened a little too late for you, it kind of did to me, then that can be remedied by giving it a third curve shape argument. Here, a negative value causes the tempo change to start sooner, and a positive value causes it to happen later. So if I give it a curve shape of, say, -6, we should start to hear it accelerate more quickly. That was pretty noticeable, I think. Now, setTempoTarget can be called at any time, not just when the session is created. So for instance, we might make this acceleration happen right after the first phrase ends. Actually, that first phrase might take a really long time at tempo equals 40. So I'm going to switch it up and make it start out fast, and then after the first phrase ends, have it slow down to tempo equals 40 over the course of 15 beats. Let's take a listen to that. Now what probably happened there actually is that it wasn't quite at tempo equals 40 after the second phrase ended. And so setTempoTarget was called again before the previous tempo target had been reached. Let's see if we can get a little bit more information about what's going on by defining a parallel process called print tempo and having it continually print the tempo and wait 0.1. And right here, we're going to fork print tempo. Let's take a look and see what we get. So it stays at 200 until the first phrase ends. Now it slows down. So it almost reached the tempo of 40, but didn't quite get there. And at the end of the phrase, it set another target of 40 for 15 seconds in the future. Now, sometimes you want the tempo to follow a more interesting path than a single acceleration or deceleration. And for that, you can use s.set tempo targets. Notice that also you can do set rate or set beat length targets. Remember, affecting any one of those three properties affects all three. If we look down at the documentation, set tempo targets, where is set tempo targets? It's right here. Expects a list of tempo targets and a list of segment durations and a list of segment curve shapes. So why don't we set a target of 60, then back up to 150, then back down to 40. Now these durations are all based on the current time. So if we say 10, 20, 30, this means that the tempo of 60 will be reached 10 beats from now, 150 will be reached 20 beats from now, and 40 will be reached 30 beats from now. This means that each accelerando or ritardando takes 10 beats. Let's take a listen and a look at the tempo printout when we run this script. Okay, it reached 60 and it's accelerating again. And it's decelerating again back to 40. Let's try making this a little bit more extreme, actually. Let's set a tempo target of 20 for the slow tempos. Now you may notice that it very quickly gets down close to 20 and hovers around 20 for a long time. And again, on the other end, as we're accelerating, it's hovering around 20 for a long time. Now this is actually an artifact of the fact that these are durations in beats, and beats go by a whole lot quicker at a fast tempo. This is why set tempo target and set tempo targets has an optional argument, duration units, which you can set to either beats or time, and it defaults to beats. If instead of using the default duration unit of beats, we say duration units equals time, these numbers now refer to 10 seconds in the future, 20 seconds in the future, and 30 seconds in the future, rather than 10 beats, 20 beats, and 30 beats. We'll run it again, and actually, I'm going to print, in addition to the tempo, I'm going to print s.time. This tells me how much time has passed since the script began. Notice that we reach a tempo of 20 exactly at time 30. And up here, we reach the tempo of 150 at time 20. And up here we reach the tempo of 20 at time 10. If we change duration units to beats, which is the default anyway, then when we run this, we don't reach the tempo of 20 until 16.5 seconds have gone by. On the other hand, if we print the beat, then let's take a look at what happens. Notice that at a fast tempo, beats fly by quickly, but at a slow tempo, they fly by very slowly. And that right there, at beat 10, we finally arrived at tempo 20. This may seem a little nitpicky, but there are times when you want to control the tempo in terms of beats and other times where you might want to control it in terms of time. For instance, if you're composing a notated score and you want to arrive at a certain tempo on bar 85, you would want to use the standard duration units of beats. On the other hand, if you were designing a 10-minute long fixed media piece that involved a gradual acceleration towards a fastest moment exactly 7 minutes in, you'd want to use duration units of time. So those are the basics of controlling tempo in SCAMP. Stay tuned for a few more advanced possibilities. Okay, so now we're going to take a look at a couple more advanced options with tempo, especially relating to when you have multiple parts going on. So here, in addition to the oboe part, I've created a cello part, and I've put the oboe part in its own function, and the cello part in its own function. The cello part just plays a few half notes, looping through a C, a G, a flat seventh, and then a C. We fork both of them and then wait forever on the main thread. If any of this is unfamiliar, you'd probably want to go back and look at the video about forking functions. So let's take a listen to this. Okay, so I'm not pretending that it's great music, but it'll do as a demonstration. So now one thing that we've already seen is that we can set the initial tempo for these parts by using the initial tempo argument in fork. So I'll set the initial tempo of the oboe part to maybe 120 and the initial tempo of the cello part to 60. Oops. Initial tempo equals 60. Let's take a listen to that really quick. So what I want to do is I want the oboe part to slow down to 60 and the cello part to speed up to 120. And in order to do that, I need access to the clock that these two parts are now going to run on. Now there's a couple different ways to access this clock. You can actually access it from the main thread because s.fork returns the clock that the oboe runs on. So I could say here oboe clock equals and cello clock equals, and then I could set a tempo target for both of them. Oboe clock dot set tempo target, let's say 200 over the course of 30 beats, and I can do the same thing with the cello clock. Cello clock dot set tempo target. I'll set the oboe to go down to 60 actually, and the cello to go up to 200. And actually in this case, I kind of want them to reach their respective tempos at the same time, but they won't do that unless I set duration units equals time, because 30 beats when decelerating from 120 to 60 is not going to be as the same as 30 beats when accelerating from 60 to 200. So I'll say duration units equals time in both cases. Let's take a listen to this. So listen for the oboe to slow down and the cello to speed up. That's probably been about 30 seconds. We can hear that the cello is going more than 3 times as fast as when it started, and the oboe slowed down to half the tempo that it started at. Now this isn't the only way to access the clock. You can also access it from inside the part by using current clock. So for instance, if we took the cello's tempo target and asked the current clock within the cello part to aim for that tempo target, that would have the exact same effect. Likewise, if we copied this line with the oboe part up here and said current clock, this will have the same effect. I mean, let's take a listen. Should hear the oboe slowing down. The cello speeding up. You don't have to listen to the whole thing. One last option is actually, as a convenience, you can actually write in the clock as the first argument to the function. And if when you're forking it, it sees that there's an extra argument here in the function, it sends the clock to the first argument. So this is just a little convenience that avoids having to say current clock, especially if you're using the clock more than once. Again, let's test it the same effect. Great. Now another convenience that we have here is that if you set multiple targets, you can actually loop the accelerando and ritardando segments. So I'm actually going to switch to saying set rate target. And I'll actually set multiple targets. And I'll ask the cello to go up to tempo equals 200, then back down to 60. And I'll ask it to do it over the course of, rate targets. A rate of 3 and back down to 1. A rate of 200, that would mean 200 beats per second, which would get a little bit absurd, and I don't want to see what would happen if I did that. So I'll have it reach a rate of 3 after 10 seconds, and then back to a rate of 1 after 20 seconds. This means it's going to spend 10 seconds accelerating, then 10 seconds decelerating. And then I can actually add one more keyword argument here, loop equals true. And if I do that, then when it's done with these rate targets, it's going to repeat the process. So it's going to keep accelerating to 3, decelerating back to rate 1, accelerating to rate 3, decelerating back to rate 1. So let's take a listen to that. So cello's accelerating a lot. Now it's decelerating. And now it should start accelerating again soon here. And here you can hear it start to accelerate. And then it's decelerating once again. So it'll keep doing this forever because we said loop equals true. Okay, so as one final advanced option, we can actually get the tempo to follow a function. So over here, I've actually drawn up on Desmos the function 1 plus 0.5 cosine, whatever, it doesn't really matter. It's a pretty cool looking function that oscillates up and down, but gradually slows down over time. Notice that it oscillates sort of between 0.5 and 1.5. So we're going to have this be a rate function. I'll go ahead and copy this. And here, for the oboe part, instead of set tempo target, I'm going to say apply rate function. And what apply rate function expects, well, we can actually look it up over here. Oh, I have it already looked up. The first parameter is a function that takes a single argument representing the beat or the time, depending on the duration units argument. So you can have this based on what time it is or what beat it is. And then it outputs the rate that we want at that time or beat. If you want, there's lots of options here. You can select a particular part of the domain of the function and loop it. There's also some stuff down here which you almost certainly don't want to mess with. But basically all we're really going to need to use is the function argument. Now, Python has something called lambda functions, which are useful in this situation. I'll demonstrate it down here. So if we were to create a function f that takes a number x and returns x squared, then we can go ahead and say f of 3, and it'll print out 9. But for really simple functions like this, you can actually do it much more quickly with a lambda expression. I'll show you how to do that with x cubed. So I could say that g equals lambda x colon x cubed. If you haven't seen this before, the double asterisk in Python is raise it to the power. And if I do this, then g of 3 is 27. So in this really short space, I was able to define a function that takes a number and cubes it. This is particularly useful when you need to pass a function as an argument to another function, which is exactly the case that we have here with apply rate function. It expects as an argument a function taking the current beat or time and giving you the rate in return. So I'm going to paste what came from Desmos, and it looks like we're going to need the cosine function. So I'm going to import the math library, and I'll say lambda t colon 1 plus, 0.5 math.cosine 2 times x to the 0.7. Oh, it should say t to the 0.7. And so this takes in a given time and processes it and spits out the rate at which we want the clock to be running at that time. And because we're using times instead of beats, I'm going to say duration units equals time. Let's go ahead and see what this sounds like. Hopefully we'll hear the oboe speeding up and slowing down. Here's the graph. Here's it slowing down again. Here's it speeding up again. Slowing down again. Speeding up again. Slowing down again. Should be speeding up again. So you can imagine that the ability to apply an arbitrary tempo or rate function could be a very powerful compositional tool. One last thing that I want to point out is that all of these rates of the forked parts are relative to the tempo or rate of the clock that forked them, namely the session. So if we wanted to here, we could say s.set rate, well, let's say tempo target 300 over the course of 40 beats. And so what should happen is that the oboe part and the cello part will still speed up and slow down on their own, but overall both of them will speed up to about 5 times the original speed over the course of 40 beats. Let's take a listen to that. You can hear the cello slowing down. But now its slowest speed is faster than it was before. So at this point, we're probably 40 beats in. It's a little hard to tell. But as you can see, they're still both speeding up and slowing down within this much faster tempo. So those are a few more advanced options. As you can hopefully see, the possibilities are pretty endless, especially when you consider that this oboe part or this cello part could itself fork a sub part that could have its own independent tempo. So there's this possibility of nesting tempo relationships within tempo relationships, and all of them can be freely accelerating or decelerating. Anyway, hope you have fun exploring that.